Hello guys, in this video I'm gonna show you how to make matrix transformation. Specifically, we're gonna do rotation. So basically, we're gonna find the matrix that can rotate any vector, in a two-dimensional space, because this is basically easy to imagine and easy to like demonstrate and teach. Okay, but of course this can be extended to like three-dimensional and even n-dimensional as well. Okay, so basically to give you an idea how to make like a rotation. If we have like two-dimensional space like that, basically x and y. If we have a point in space like this one, let's assume this is 1 1. Okay, it's like a vector. We can connect it to the origin 0 0 and become like a vector. So when we say rotate, we're gonna rotate, with certain like angle. Okay, so basically, for example, we can rotate like with an angle theta, for example, and our new vector, okay, will be in that new like location. Okay, so basically this point here will move with that new point. Okay, so 1 1 will move, for example, to x and y. So we're gonna start first by some like specific cases, easy cases, basically special cases, corner cases, in which like the angle is like known and doable to do like easily right now. So first case is rotation about the origin with 90 degrees, okay, in a clockwise direction. So rotation about the origin with 90 degrees, okay, and clockwise. Look, guys, the general like term is counterclockwise, you know. So the positive direction of any angle, when we say, for example, the angle is 90 degrees, that means we moved from, for example, the x-axis to y-axis because this is 90 degrees. And as you see, the rotation of the movement is counterclockwise, okay? So to differentiate, we have to know, but if I just mention 90 degrees, that means it's counterclockwise because this is the default direction of the rotation, counterclockwise. This will give you like positive angles. Moving it clockwise, it's actually negative angles. Okay. Okay. So let's see how to do that. Okay. So I'm saying we're gonna rotate a vector. Okay, in a clockwise direction that way. Okay, with 90 degrees. So what we should do basically is we're gonna do like this scheme. We're gonna do it like 4 times, maybe 5 times even, with 5 different cases. I'm sure by the end of these 5 times, you're gonna be like expert how to do that by yourself. So let's do that. So basically, let's first remove that thing here. That's X. That's Mr. Y. Okay. So what do we need to do? First, to know, like, we're gonna start by a trick, and we're gonna build on it. Okay. What if you have a vector, okay, x and y, for example, x and y, and we're gonna see what the identity matrix will do for that vector. So if we multiply this vector by the identity matrix, which is 1 0 0 1, what's gonna happen? So it will stay the same, because any matrix multiplied, or any vector multiplied by the identity matrix, will give you the same matrix again, okay, or same vector again. Okay, that means if you have like the xy here, a point, a vector, and you multiply it by 1 0 0 1, the identity matrix, it will stay the same. It will not rotate or not reflect, as we're gonna learn in the future. So it will stay the same. Okay, but let's like just look here. What is this identity matrix? It's actually 2 vectors. This is number 1, and this is number 2. What is the first vector? First column, 1 0. What is this basically? 1 0 is maybe here, like this is just a point with the x-axis, which with x coordinate equal to 1, y coordinate equal to 0. And what is the second column here? It is like another vector, which is 0 and 1, x equal to 0, y equal to 1. So it's basically a point on the y axis, okay? Here, 0 and 1. So the trick that we're going to do, we're going to forget about what basically the point we want to like rotate or reflect or whatever. Okay, we're going to look at these two vectors, 1, 0, the identity matrix, and 0, 1. And see, and based on these two vectors, we're gonna do like the reflection or the rotation upon these vectors, and we're gonna deduce the matrix that is gonna do the rotation or reflection for the desired point based on the results that we're gonna get from rotating or reflecting these two vectors, 1, 0, 0, 1. Okay, and we're gonna start by our first example, rotation about the origin with 90 degrees counterclockwise. So let's see what's going to happen to the first point. So let's go back to like our normal color here. Okay, first point is 1, 0. Forget about like the 1, 1. So I'm going to go back here to let's assume we wanted to rotate 1, 1. Okay, so we're going to remove this extra x and y here, and I'm going to go back to red. It's 1, 1. It's the point we want to rotate or the vector that we want to rotate. Okay, so we're going to apply the rotation first on 1, 0 and the 0, 1. And this rotation will give us the matrix that's going to be multiplied by 1, 1 and make the rotation 90 degrees clockwise. Okay, clockwise means this direction. So we want to move or rotate 1, 0, 90 degrees. Okay, so this one will rotate like that. And remember, it's 90 degrees. This is 90 degrees. So the 1, 0 will end up at this point, which is 0 and minus 1. So number 1 here, or like number A, whatever, or asterisk 1, 1, 0. When we rotate it like 90 degrees clockwise, will end up at 0 minus 1 without any thinking. That's basically the rotation matrix that we need. So we're going to replace the 1, 0 with 0 minus 1. The new location of the 1, 0 when we rotate it 90 degrees clockwise. Good. 2 asterisks. Let's make it with another color, like red. Okay. 2 asterisks. What's going to happen when we rotate the 0, 1, the second this point, 90 degrees clockwise? So we're going to take this vector and rotate it like that. So it will end up at 1, 0. So the 0, 1, when we rotate it with 90 degrees clockwise, it will end up at 1, 0. Again, so you replace in the identity matrix, you replace 0, 1, this column here, you replace it with 1, 0. And that's it, guys. This is basically the rotation matrix required. The rotation matrix that's gonna do 90 degrees rotation clockwise direction. Let's apply it. Let's apply it. So go back to our normal color here. So let's apply 0, minus 1, 1, 0, 2, 1, 1. I'm gonna just multiply them like blindly and look at the result and reflect, because we can do that even without like finding or multiplying or finding the transformation matrix, but rotation matrix. But I'm gonna do it first just blindly, then we verify that. So when we multiply these 0, 1, 1, 1, it will give us 1. minus 1, 0, and 1, 1, it will give us minus 1. So when we do the rotation, let's now do that here with another color. Let's do it like with green, for example. So 1, 1, when we rotate it 90 degrees clockwise, it will end up at this location, 1 minus 1. 1 in the x and minus 1 in the y. So it will be here. Let's like take this away. So it will end up here. 1 in x, this is 1 in x, and minus 1 in y. So it will end up here. So that's the new location of the vector when we do 90 degrees clockwise. Is this really the case? Let's check that, because we can do that even without multiplication. So we want to rotate 90 degrees. Remember, this is 1 and 1, right? So this means this is 1, and this is also 1. So this triangle here has like equal like sides. So this is 40, this is 90 degrees. So this actually, this angle is 45 degrees. So this angle is also 45 degrees. So basically, when we rotate 90 degrees, we're gonna rotate first 45 degrees until we reach the x-axis. It's another 45 degrees. Then we're gonna end up in that location. And this angle here is 90 degrees. 45 plus 45. That's correct, right? So just verified that what we did like geometrically without any multiplication and stuff can also be deducted using this way. So the basic, the concept here is to apply first the rotation that you want on the identity matrix, the two vectors of the identity matrix, 1, 0, 0, 1. You want to get the transformation matrix, multiply it to get the rotated vector. Okay, number 2, for example 2. We're going to do the same exactly, in another example here, and you're going to be expert. Be sure of that. Number 2. So rotation this time 90 degrees counterclockwise, which is the original or the default direction of any angle. So rotation 90 degrees counterclockwise. If I didn't say like the direction of the rotation, it by default it's counterclockwise. This is default rotation of any angle. Okay, so again we have like our example, same example in all cases. So we have y and x. Again, 1 and 0, 0 and 1, and our point that we're gonna always do the rotation for is 1, 1. Okay, so we wanna find the transformation matrix. We're gonna apply to the 1, 0 first. So when we do this for 1, 0, let's do this with like red, for example. The 1, 0, 90 degrees counterclockwise. So counterclockwise is this direction. So we're gonna move 90 degrees. So this is, remember, this is 90 degrees. So it's gonna be end up here. So the first column 1, 0 in the identity matrix will be 0, 1. That's the new location of the 1, 0. How about second like point 0, 1? Let's do it with green, for example. So we're gonna move 90 degrees. Remember, this is also 90 degrees and it's counterclockwise. So we're gonna move like that. So we're gonna end up here at minus 1 and 0. Minus 1 and 0. That's it. That's your point, my friend. Let's do like the verification. Let's multiply it by our vector 1, 1. Again, we wanted to make the rotation of 1, 1, but we stopped by the identity matrix. So let's multiply these two together. 0 minus 1, 1, 1. This will give us minus 1. 1, 0, 1, 1 will give us 1. So let's now check what we do in algebra should be verified by geometry. So let's try another color, like for example, the magenta in this case or the purple. So remember, we want this vector here, 1, 1. We wanted to rotate it 90 degrees counterclockwise. So we start here. We should go 45 degrees, another 45 degrees. So it will end up in that location. 45 degrees to the left of the y-axis. Remember, this is 45 degrees, right? So it's going to end up here. Another 45 degrees. So that's the new location. What is that point? That point is -1 in x and 1 in y. -1 in x and 1 in y. We verified it. Good. We're going to be expert. Be sure about that. Number 3. Let's try the 180 degrees. And for 180, it doesn't matter. You can do it like counterclockwise or clockwise. Both are the same, okay? Because you're gonna end up at the same location if you move like 180 degrees clockwise or counterclockwise. You're gonna end up in the same location. Okay, we're gonna verify this. So let's again draw like our axes here. So let's first write the question. So rotation 180 degrees. Let's make it counter first. Then we're gonna verify later that counterclockwise with 180 degrees is equal to clockwise. So let's draw our axes here. Here are they, X and Mr. Y. So we start first by 1, 0. So for 1, 0, when we rotate it counterclockwise 180 degrees, let's do this with like red. So we're gonna move, remember this is 90 degrees. And this is also 90 degrees. So both are, if you add them, it's 180 degrees. So we're gonna move like that. So we're gonna end up at that location. Remember, you move it like 180 degrees. So you move it. This is 90, another 90. You end up on the negative x-axis. Okay. So the 1, 0 reaches. What is that one here? This is -1 and 0. -1 in x and 0 in y. Good. That's the first point. Let's do the second point, or the second vector, which is the 0, 1. We want to move it 180 degrees again. So 180 degrees counterclockwise. But here again, you're moving counter is like moving clockwise because both will end up in the same location. So let's do that. 180 counterclockwise, so same location. We're gonna move like that. We're gonna move like that. Oh, we ended up here. Okay, that's very good. What is that one here? This is 0 and -1. 0 and -1. Okay. Before we move forward, if we did that in clockwise, did we get the same stuff? Yes. Let's check that. So let's first start by 1, 0. If we move 1, 0, let's do this with another color, just to make sure. Let's try like, I don't know, like orange, for example. So first we followed like the red like curve here because it's counterclockwise. If we move it like clockwise, it will be like that. Same location. Okay. Just remove that now. Okay. Let's now do the green. So 0, 1, we moved first in that direction. Now we're going to move in that direction. So let's do it. So we move 180 degrees. We're going to end up in the same location. Okay. That's why for 180 degrees, it doesn't matter. Clockwise is like counterclockwise. Okay. Now we do our multiplication because originally we wanted to transform 1, 1. 1, 1 here. Okay, we multiply this. -1 and 0, 1, 1. This will give us -1. 0 minus 1 and 1, 1 will give you -1. Multiply them together. Now we check geometrically. So we wanted to move 1, 1, 180 degrees. We're going to rotate it 180 degrees. So we're going to do that. Let's check what color we do. We do the purple again. Okay. So we move, it doesn't matter, but we're going to do like counterclockwise. So for counterclockwise, Remember, we want to move 180 degrees. So look, this is 45. This is 90. So 90 plus 45 is 135. Minus 180, 45. So we wanted to move another 45. So when we move like that. When we start from 1, 1, we should reach that point here. Okay? So minus 1 and the minus 1. So that's the new location of the point 1. Okay? And remember, moving counter for 180 is like clockwise. Okay? So again, for clockwise, this is 45. This is 90. 90 and 45 is 135. It needs another 45 to reach like 180. That's a 45. So again, it will end up in that point here, which is minus 1 and the minus 1. So we are good. Okay. Finally, number 4, rotation 27 degrees. Rotation 27 degrees clockwise. You can do it yeah, like with I'm gonna leave it like an exercise for you, but I'm gonna do it with another way. So moving 270 clockwise is like moving 90 counterclockwise. Let's check that. I'm gonna do it that way, and you can verify with like the normal procedure. So let's draw the. This is 1-0. So we wanted to move 270 clockwise. 270 clockwise, that means 90 degrees, another 90 degrees, because 270 is equal to 90 plus 90 plus 90. Okay, that's first 90, second 90, third 90. So basically, when you move like that, you're gonna reach here at 0, 1. Okay, but this if you move like clockwise. If you wanted to move, but we can reach the same point if we move just 90 in counterclockwise, right? So if we move like that, this is 90 in a counterclockwise direction, you're gonna reach the same point again. Okay, so that's equivalent to rotating 90 degrees counterclockwise. Counterclockwise. And I'm gonna, do it like that. But we did like the 90 degrees counterclockwise before, right? So let's see. Where is it? Counterclockwise 9, this one here, number 2. So we know the matrix. It's 0 minus 1, 1, 0. 0 minus 1, 1, 0. 0 minus 1, 1, 0. 0 minus 1 and 1, 0. Let's check again just to verify. Yeah, 0 minus 1 and 1, 0. Okay? So we will multiply it by 1, 1. I'm going to check again, by the way, so don't worry. So 0 minus 1, 1, 1 will give you minus 1. 1, 0, and 1, 1 will give you a 1. Okay, so let's do that. Let's like remove all that stuff here. Okay, let's do it like stroke. Yep. Okay, I'm going to do it directly. So that's the 1, 1. That's the vector 1, 1, and we're gonna move it like 27 degrees. Okay, 27 degrees clockwise. So that's a 45. Okay. Then 180. So 45 plus 180. Let's add them together. Okay, this is 5. 4 plus 8 is 12. So 225. Okay, we want 270. 270 minus 2 to 5 is basically 45. Okay, so we need another 45. You need another 45, basically that line here. Okay, so when we move when we rotate that line 27 degrees counterclockwise, we're gonna end up at that point here, which is -1 and 1. Very good. Now, let's do the trick. If we rotate 90 counterclockwise, do we reach the same location? Yes, let's see that. So we're gonna do it, for example, with red. So remember, this is 45, this is another 45 here, but we want 90, so another 45 required, which is this one here. So we're gonna reach the same point, right? So that is a trick that you can do. I advise you to always use counterclockwise, okay? Or basically whatever you see convenient or like more yeah, convenient to you, just use it. Okay, let's now do the general like rotation with any theta. Now we have to do like the general like rule, okay, for any theta. So if we have number 5 here, rotation theta degrees, okay, counterclockwise. Basically, if I didn't say anything, that means it's counterclockwise, okay? So like, but just write it like for the sake of like argument, counterclockwise to be more clear for you, okay? So for any theta, what's gonna happen? Again, I'm gonna follow the same rule, okay? We're gonna start by 1001. See what's gonna happen if we rotate like with theta 10 and just theta another theta like 01, and just create the new or drive like the transformation matrix or the rotation matrix for theta rotation. Okay, so let's do that here on the axis. Okay, so that's our y-axis and that's our x-axis. I'm gonna do them big this time. Okay. Okay. This is, for example, 1, 0. Of course, it's so big, but you know. So I wanted to rotate first the 1, 0 with like a theta angle. Okay. So let's assume it's gonna rotate and, for example, reach this point, for example. Okay. That point, for example, has two like indices or coordinate x and y. We don't know x, we don't know y. What we know is that this rotation was a theta angle. Okay. Okay. Remember the length of that like vector is 1. And when it rotates, it preserves the same length. When I rotate this like with a theta, it's same vector. Okay. So that's also 1. And remember that's like a right angle here. That triangle that we create has a right angle. Okay. So, and the hypotenuse here is equal to 1. Okay. So that's, remember, x, y, and that length here is x. Remember, the whole length is 1. So that's very like we should. So that's the point. The point has like rotates like that. So this one here is 1. Okay. But part of it is x. Just note it here for you, not to confuse yourself. Okay. So let's find x and y. Once we find x and y, we find the new location, right? So x equal to the hypotenuse, which is 1 cosine theta, and y, which is in front, the side in front of the angle, is equal to the hypotenuse 1 sine theta. So basically x is equal to cosine theta, y equal to sine theta. Okay. Sometimes they write it just CNS, you know. So x equal to c, we know it. This means it's cosine theta, and y equal to s, we know this is sine theta. Okay. Good. So we know now the first column of the rotation matrix. Okay. So 1, 0 has become x and y, CNS, or cosine theta, sine theta. Okay. Now let's do the other like coordinates. Let's do it with red, for example. Okay. As long like here, this is 0, 1. So 0, 1 will rotate. For example, here, same length. Again, this is, for example, x and y. Okay. This is again 1. This is also 1. This new point has two coordinates, x, y, as I said. This is, for example, y. And this here, I'm sorry, we have it already. This one here is x. Okay. So again, x. Oh, this is theta here. This is the angle theta. X now is in front of the angle. So x now is 1 sine theta. Or sine theta. We're going to call it S. Y. This basically this length here. This is y. Let's remove the curve inside for you guys. Okay. Y now, this is theta, is the 1 cosine theta. 1 multiplied by cosine theta equal to cosine theta, or basically C. Okay. But one thing here that I just missed, but thank God I remembered it. So basically x here is negative. Okay. Is what is negative. So that's basically -1 minus theta minus sine. Yeah, minus sine theta. So we're gonna put this minus just to compensate for the fact that this is in the negative x-axis. Okay. So the 0, 1 has rotated to minus S and C. Okay. So basically now the moment of truth, or the conclusion here, or the moment of truth. So the rotation matrix with angle theta is equal to CS minus S and C, or you can write it completely cosine theta minus sine theta, sine theta, cosine theta. Okay. The moment of truth comes when you check that. This is the general rule, right? The general like rotation with any angle theta. If we put 90 or minus 90 or 270, 180, we should just get what we did before, right? In the beginning of this like lecture. So let's start to check that. So number 1, or check 1. Check number 1 here. Theta equal to, let's do 90 degrees counter clockwise. Okay. I'm going to do it first here just to compensate with theta equal to 90 and just to check versus what we get like here. Okay, in that case, R 90 counterclockwise, okay, equal to cosine 90 minus sine 90, sine 90, cosine 90 equal to, this is easy, cosine 90 is 0. Good. Sine 90 is 1. Sine 90 is 1, so minus 1. 0 minus 1, 1, 0. 0 minus 1, 1, 0. Let's see. 0 minus 1. This is the one. Yeah. 0 minus 1, 1, 0. So we are good. Okay. Check number 2. Check number 2. Theta equal to 90. Let's do it now clockwise. Okay. So R 90 clockwise equal to. Okay. 90 clockwise, that's very important here to note, because 90 clockwise is actually 270 counterclockwise. Okay, so let's draw it. So if we have like an coordinate like that, if I want to move here 90 clockwise, I'm gonna move to that point, or this is 90 clockwise. I can move also in that direction 270 degrees counterclockwise, right? Because theta here in this general formula is assumed to be measured from the in a counterclockwise direction from the x-axis. That's very important. So this will be cosine 270 minus sine 270, sine 270, cosine 270. I don't like to speculate, so let's just do it online. So let's like just find sine, cosine calculator website, whatever, should be easy. Okay, so we need sine 270. That's minus 1. So minus 1 minus minus here will be positive. So this is positive 1. Sine 270 minus 1. Now we need cosine. So let's do it. Cosine calculator, cosine 270. That's basically 0. Okay, so we end up with 0, 1, minus 1, 0. 0, 1, minus 1, 0. Let's check. We have it. 0, 1, minus 1, 0. So we need 90 clockwise, 90 clockwise. 0, 1, minus 1, 0. 0, 1, minus 1, 0. That's also correct. Okay, check number 3. Check number 3. Theta equal to 180, and here clockwise equal to counterclockwise. There is no reason to say count, because the rotation with 180 degrees clockwise is equal to the rotation 180 degrees counterclockwise. We did this before. Okay, and of course, if you move 180 counterclockwise, it's like 180 counterclockwise. You can do it in this way, like what we did with 90 and 270. Okay, so R 180 counterclockwise equal to counterwise here. Clockwise, I'm sorry. So that's cosine 180, sine 180, sine, sorry, minus here, sine 180, and cosine 180 again. I don't like to remember, so cosine 180 minus 1, so minus 1, minus 1. And we need also the sine, so this is a calculator online that I'm doing, and just search for it, sine 180. That's 0. Okay. So we have minus 1, 0, 0, minus 1. Minus 1, 0. Yup, minus 1, 0, and this one, 0, minus 1. Okay. The 270. We did it before. So this is the 270. It is basically the clockwise direction. 90 clockwise direction is basically 270 counterclockwise direction. So we did it before. Okay. That's it, guys. So that's basically like the general formula. Now, lastly, just before I move on to the reflection in the next video, we want to do like special case. If we want to do a rotation, successive rotations, like 2 rotations, for example, with 2 different angles, theta and phi, for example, or phi, whatever you call it, So number 6, 2 successive rotations. Like theta, then phi or phi. Some people say it phi, some people say it phi. So that's basically, the coordinate. This is what we wanted to do. Assume you have a vector x and y. Okay, we're gonna rotate it like with two angles, two times. First, we're gonna rotate it with theta. They're gonna give us like x1, y1. Then phi or phi, another rotation, which gives us the final calculation xf, x final, y final. Okay. So what we're gonna do here? That's very simple one, by the way. Maybe look complicated, but it's very simple. Because what we do, you do two rotations. You multiply twice. Okay. So let's assume the vector is called the v vector. So first, we will multiply this vector from the left with the rotation by theta. So r theta. Okay, and the result of that will be multiplied again from the left. Remember, guys, we always multiply from the left. You see, from the left. Let's go back. Yeah, from the left. From the left. You see, this is the vector that we want to transform or rotate, and the transformation matrix, the rotation matrix, is on the left. So we're gonna multiply by r phi or r phi. Okay, so we can multiply it or write it in this way: r phi or phi, r theta, then phi, or r phi, r theta, x and y. Okay, so let's take an example for that. But before I take the example, this is the first way to do it, right? But remember, if you move a vector or you rotate a vector with two angles, you can just make it in one step, right? With theta and phi. So rotating with theta, then phi is actually rotating it as just one step with the angle equal to theta plus phi. Okay, so that's equivalent to rotate one time with angle equal to theta plus phi. So the angle itself is called theta plus phi. Okay, so for example, if theta is equal to 30, phi is equal to 60, you can do rotation by 30, r30, then r60, rotation by 60. Or you can just make it like r30 plus 60, which is r90, just one step, 90 degrees. Okay, so r theta plus phi v, or r theta plus phi x and y. So what is r theta plus phi? So again, let's get it. So r theta plus phi, basically you're gonna apply the same like matrix here, c minus s is c. So sine theta plus phi minus sine theta plus phi, sine theta plus phi, and cosine theta plus phi. Someone might ask, if we make it r theta separate and r phi separate and then multiply them to each other, are we gonna get this? Yes, you're gonna get this, exactly this. Okay, but I'm gonna leave it to you. Very easy. Okay, so let's take an example for that. So rotate the vector 1, 0 first with angle theta equal to 30. If no direction is mentioned, that means counterclockwise. Then another angle equal to 60. Why I choose this? Because it's very easy to drive it, because it's 90 degrees at the end of the day, right? I'm gonna do it in two ways. Two steps are R30, R90. Then I'm gonna do it with just one step R90. Okay. So First, we're gonna multiply R30 with the vector R30. So cosine 30 minus sine 30, sine 30, cosine 30. We're gonna multiply this by 1. Okay. So cosine 30 is, I believe, square root of 3 over 2. Sine 30 is half. So this is minus half, half, square root of 3, 2, multiplied by 1, 0. That's equal to, let's do it. This is square root of 3 over 2. And that's square root of 3. It's half. Yes, half. Then you take that and you multiply it by R60. So R60 multiplied by square root of 3 and half equal to R60 is cosine 60 minus sine 60, sine 60, cosine 60. And the vector now square root of 3 over 2 and half equal to cosine 60 is half, sine 60 is square root of 3 over 2 and half here. And here we have square root of 3 over 2 and half. Let's do that. So the first item half multiplied by square root of 3 over 2 plus or minus here. It will be minus square root of 3. So this will give us 0. You can do it yourself and verify. Then 3 over 4 plus 1/4. Okay, which is basically 0 and 1, because this week 3/4 plus a quarter is just 1, 4 over 4, right? Okay, let's verify this because it's easy, very easy to verify. So that's basically, no, that's not good. That's basically our vector here, 1, 0. And we wanted to rotate it by 30 is 90, right? So we moved it by, for example, assume this is like 30 here. Then this will be 60, right? So at the end of the day, it will move to this location, to 0, 1, right? And you can do it directly with 90 degrees, right? So you can say R90 multiplied by 1, 0 equal to cosine 90 minus sine 90, sine 90, and cosine 90, and our vector was 0. Cosine 90 is 0, sine 90 is 1. That will be minus 1. There is a minus 1 before. And 1, 0. Let's do that. This is 0 plus 0, which is 0. And 1. Okay, we just verified it. So we verified it using the addition directly one step or 2 steps, or even geometrically if you do it like 2 steps like that. And the next time we're going to take like the reflection. Thank you very much for watching, and see you in another video. Bye-bye.